Okay, here we have the limit as x approaches 1 of the expression x squared minus 2. Now, it turns out this limit is extremely easy to evaluate upon recognizing that this expression right here is a polynomial function. Evaluating this limit is easy because we have a limit law for dealing with polynomial functions. Namely, if we're trying to find the value of the limit as x approaches c of some polynomial function p of x, we can just plug this value of c into the function in question to arrive at p of c, which is the value of the limit. So upon seeing this as a polynomial, I can just plug in 1 in for x to arrive at 1 squared minus 2, or negative 1. That's the value of the limit. Graphically, whenever we can evaluate a limit as x approaches some c of some expression by simply plugging in that value of c into the expression, we say that this function here is continuous at that value of c. Hopefully this seems natural, as if we were to graph a function like this function here, f of x equals x squared minus 2, this statement about the limit's value tells us something about the behavior of this function when x is near 1, namely that we can get arbitrarily close to a height of negative 1. It does not, of course, tell us anything about what happens at 1, so we leave that for the moment as an open circle. But again, just what happens near 1, so we've indicated that with these little tails. They might be pointed up or down depending on the actual behavior of this function, but the point is they're very close to a height of negative 1 when x is sufficiently close to 1. So this is the graphical information we get from the limiting value, but of course with this particular function we can plug 1 in and evaluate f of 1, and we get negative 1 again. It's the same calculation we saw here, which means this hole is really filled in the complete graph of f. And now you can see that around 1 we can draw the function with a continuous stroke of our pen. So again, when the limiting value of a function and the actual value of the function at a particular c value agree, we say the function is continuous there, or equivalently, in this case anyways, that 1, negative 1 is a point of continuity on the graph of this function x squared minus 2. So the value is negative 1 for this limit, and its graphical interpretation is we have a point of continuity on the graph. Okay, here, notice we have the limit as x approaches negative pi of the expression absolute value of x minus cosine of x. Now the key thing here is to realize that the expression you're taking a limit of is a difference of two functions, the absolute value of x and cosine of x. And we happen to have a limit law that deals with taking limits of differences of functions. What this limit law tells us is that the limit of a difference can be expressed as a difference of limits. Essentially, I can look at the limiting value of this expression and the limiting value of this expression as x goes to negative pi and subtract them, and that should be the value of this limit. So let's do that. Slide that to the side. This should equal then the limit as x approaches negative pi of the first function minus the limit as x approaches negative pi again of the second function. If you want to put brackets around those, you can. Notice how we started off with a larger limit and we broke it into two smaller limits, which hopefully will be easier to evaluate. Now, what is the value of the limit as x approaches negative pi of the absolute value of x? Here again, limit laws come to our rescue. Notice the limit as x approaches c of the absolute value of x is simply the absolute value of c. So in this particular case, we just want the absolute value of negative pi. So slide that to the side. So this first piece should be the absolute value of negative pi. And then we need this second piece. Here again, this is the limit as x approaches some value here of a simple function, cosine of x. Simple enough that we have a limit law for it. Look down here at number 6. The limit as x approaches c of cosine of something is cosine of that c there. Cosine of x is cosine of c. So again, all we have to do is plug this guy in for our value of x. So this should be cosine of negative pi. The limits are gone now. We're just evaluating things. That, of course, is positive pi, and the cosine of negative pi, of course, is negative 1. So it looks like this is pi plus 1. Now, while we justified this step by step with the limit laws, essentially what we did to evaluate this limit was to plug in negative pi into this expression to arrive at this. When you can do that, we say this function is continuous at this value. Or in the context of this particular limit, we can say that this point here, negative pi, notice that's what x was approaching, and pi plus 1 is our y-coordinate. Note that's the value of the limit. That's our expected height of the function, barring any knowledge of what actually happens at negative pi. We can say this point is a point of continuity on the graph of y equals this expression here, which just duplicates this. Okay, so that's the value of the limit, and that's the graphical interpretation of what's going on. Okay, in evaluating this limit, our first impulse might be to say, well, look, we're taking the limit of a complicated thing here. I wonder if we could break it into simpler limits somehow. Perhaps, since this is a quotient of two functions, maybe I can use that limit law that deals with quotients of functions, this one right here, to split up this limit of a quotient into a quotient of limits. Well, that would be great, except there's a condition we have to meet to be able to apply this, and that is the limit of our denominator must not be 0. So, going back over to here, and looking at our denominator, when we ask the question, and we can do this in our heads here probably, what happens in the limit to x plus 3 as x approaches that same negative 3 that we have it approaching above? Well, notice this right here is a polynomial function. And we've seen we can find limits of polynomial functions just by plugging in this value into that function. So we'd have negative 3 plus 3 or 0. Uh-oh. It looks like we can't apply this limit law for quotients of functions. We haven't met the condition. So we're going to have to find another way. Well, going back to the original limit, what can we do? What looks familiar? What change could we make? Notice this x squared minus 9. It should stand out as a sore thumb. We know how to factor this, don't we? Let's see where that leads. Certainly, this is the limit as x approaches negative 3 of, and now factoring the top, that'd be x plus 3 times x minus 3, right? That's a difference of squares over an x plus 3. Now, what's our temptation here? We would really like to cancel the x plus 3's, right? Can we do that? Is it true that the limit of all this is the limit of simply x minus 3? Let's think about the graphs of these two functions, this one and this one. If we were to graph this x minus 3, or y equals x minus 3, of course the graph of that is familiar to us. It's a line, right? In fact, it's a line through negative 3 on the y-axis and 3 on the positive x-axis. Now let's consider the graph of this, the graph of x plus 3 times x minus 3 over an x plus 3. Think about this. For many, many values of x, for example, when x is 7, this is 10 times 4 over 10. The 10's cancel. When x is 2, this is 5 times negative 1 over 5. The 5's cancel. When x is negative 5, this is negative 2 times negative 8 over negative 2. The negative 2's cancel. For many, many values of x, in fact, all values of x except for 1, this x plus 3 will cancel, leaving just x minus 3, which means the graph of this should be identical to the graph of this for all of those x values. But there is one point, one value of x, where this function differs from this one. And that is when x equals negative 3. Because you see here the denominator would be 0, yielding an indeterminate expression. So if we were to graph this, we should see a line identical to the green one, except for at negative 3 on the x-axis, there is no corresponding point on our graph. We have a little hole here. Now, intuitively, looking at these two graphs, the limit behavior at x equals negative 3, or as x approaches negative 3, on both should be the same. We should be getting arbitrarily close to the same height when x gets close to negative 3. And indeed, we have a limit law to that effect. If two functions agree everywhere except for at one value, x equals c, and you look at the limiting values of those two functions as x approaches that very same c, they should be equal. Which tells us, yes, indeed, it is okay to cancel from here to here. So let's mark that as such. Now, when we get to here, we're taking the limit as x approaches negative 3 of what kind of thing here? This is a polynomial function. And we've seen before, we can evaluate such limits just by plugging in the corresponding x value that we're approaching. So this becomes negative 3 minus 3, or negative 6. And that's the value of the limit. Graphically, however, remember, when we're looking at this function right here, it graphs like this, right? This was just the factored form of this. And we have a hole at negative 3. This is because the limiting value existed, but the value negative 3 was not in the domain of this expression here. When that happens, or when the limiting value should disagree with the value of this function at this point, in either one of those cases, we say we have a hole in our graph. Specifically, with regard to this limit, we can deduce that the point negative 3, negative 6, notice the negative 6 is the height here. If we were to mark it on our graph, there it would be. Negative 3 is the x value we're approaching. Negative 3, negative 6 is a hole in the graph of that expression right there. So that's the value of the limit, and that is the graphical interpretation of what's going on in this function. Okay, here we have the limit as x approaches 0 of some function f of x, where f of x is defined above as a piecewise defined function. Now remember, the limit of f of x as x approaches something tells us about the behavior of this function when x is very close to this value. However, in this function, in the one we have defined, even though we're very, very close to x equals 0, it makes a difference which side of 0 we are on. If we are to the left of 0, f of x is defined to be this function right here. If we are to the right of 0, f of x is defined to be this function. If this limit is to exist, then the limiting values of this function as we approach 0 from the left side, and the limiting value of this function as we approach 0 from the right-hand side need to agree. We have a limit law to that effect. It's right here. The limit as x approaches c of f of x is only going to be L. This is only going to exist if the limit coming in from the left of f and the limit coming in from the right of f agree. So let's break this up into the two cases we need to consider. 1, what is the limit as x approaches 0 from the left of f of x? And 2, what is the limit as x approaches 0 from the right of f of x? Okay. Well, now, if we're assured that we're only ever going to be considering x values to the left of 0, I can replace f of x with something equivalent. If I'm to the left of 0, that puts me in this condition right here, and so f must be x plus 2 for all of those cases. And so we have the limit as x approaches 0 from the left of x plus 2. And of course, this is the limit of a polynomial. A one-sided limit of a polynomial. Same rule as always applies. We can plug in this value into the polynomial to evaluate the limit. This is 0 plus 2 or 2. Okay, so I'll put a little dotted box around that. That's not necessarily the value of this limit yet, but it certainly is the value of the one-sided limit on the left. Down here, same deal. If I am assured I'm always to the right of 0, I'm always a little bit bigger than 0, even though my x is getting very, very close to it, then that puts me in this condition. And so f of x is identically 2 in all of those cases. So I can write limit as x approaches 0 from the right of simply 2. But this, of course, is a limit of a constant, which must be that same value. Okay? So, what does this mean? This limit exists only if both of these limits exist and agree in value, and sure enough, they do. So we can say with surety that this is 2. Now, graphically, what's going on here? Notice, to evaluate these limits, we never used this middle piece that tells us the behavior of f of x at x equals 0. And that was expected. Limiting values as x approaches some c don't care what f does at c. What I can glean graphically from this statement right here is the following. My function, shown here in blue, gets arbitrarily close to a height of 2, provided I stay sufficiently close to my x equals 0. With the possible exception of what actually happens at 0, which this doesn't say anything about. But we know what happens at 0. When x equals 0, f of x is 0, which means this point is also on our graph. Now, exactly what happens with the rest of the graph for these other x values really depends upon the nature of the other functions involved in these two pieces. And sure enough, you can see that when x is bigger than 0, we're talking about a constant function. So this actually shoots out straight like that. And when x is less than 0, we're talking about the function x plus 2, which looks something like this. Okay. But even before putting those two other pieces in more fully, we can see what's going on as x gets very, very close to 0. We have a hole right here at 0, 2. Just writing it out here, again, 0 coming from the x value we're approaching, and 2 being the value of the limit. Okay, so we have a hole in the graph of y equals f of x. This is the value of the limit. This is the graphical interpretation of what's going on in this function near 0. Okay, let's take a look at this example. We have the limit as x approaches 2 of the polynomial function x squared minus 4 divided by the absolute value of x minus 2. Now, at first blush, this appears to be the limit of a quotient. And we have a limit law for dealing with limits of quotients of functions. Here it is right here. we can re-express those things as quotients of limits, sometimes, if the limit of the denominator, as x approaches the same c, is not 0. So, what happens in our case? What is our denominator doing? We're asking the question, what is the limit as x approaches 2 of the absolute value of x minus 2? Now, you should get to the point where you can answer this question in your head, but just to be explicit about it this time, notice this is the limit of a composition of two functions, a polynomial function, x minus 2, inside the absolute value function. And we have some limit laws that deal with compositions of functions. Let's look at this one right here at the bottom. Notice that if you're looking at the limit of a composition, f is the outer function. For us, that's the absolute value. That this function here can be pulled outside of the limit, provided this criteria is met. This would say then, in our case, the outer function again, f is our absolute value function, that the limit as x approaches c of the absolute value of x must be the absolute value of c. But we know that to be true. Look, that's one of our other limit laws. There it is right there. We can evaluate the limit of the absolute value of x as x approaches c just by plugging c into the absolute value. So, that means we can pull the absolute value here outside of the limit. To get this. Now we're just looking at the limit as x approaches 2 of a polynomial function, and we know how polynomial functions behave. We can just plug in this 2 in here to evaluate the limit inside the absolute value. So this becomes absolute value of 2 minus 2, or of course absolute value of 0 or 0. So the denominator is going to 0. Bummer. Remember, we could only use this quotient rule for limits if the denominator was not going to 0. So we're going to have to find another way. You might notice that the top, if you look at its limiting value as x goes to 2, of course this would then be the limit of a polynomial function, also goes to 0, doesn't it? 2 squared minus 4, plugging in since it's a polynomial. When you see this 0 over 0 limiting behavior, it sometimes suggests that we might have a common factor across the top and the bottom that could be canceled off somehow to make progress towards evaluating the limit. That, in combination with the fact that the numerator is fairly easy to factor, suggests we do just that. Let's factor the numerator. So this should be equal to the limit as x approaches 2 of this being a difference of squares. That's just x plus 2 times x minus 2. And of course that's sitting over the absolute value of x minus 2. Now at this point you should have an urge, right? You see these two x minus 2's? You really want to cancel something there, don't you? But remember, this is inside absolute values. And because of that absolute value, this may or may not equal x minus 2. It might be different in sign from this. You see, the absolute value function is really a piecewise defined function in disguise. Recall its definition. If what's inside of it is greater than or equal to 0, well then the absolute value doesn't do anything, right? It just leaves the thing that's positive inside of it alone. It returns simply x. However, if x is less than 0, if you're talking about a negative value of x, well then the effect of the absolute value is to change its sign, to change it back to a positive. How else might you change a negative value back to the corresponding positive value? Well, you could multiply by -1 to get negative x. So then the question becomes, when is what's inside the absolute value positive, and when is what is inside of the absolute value negative? Well, to be positive, this x had better be bigger than 2, right? In other words, we need to be to the right of 2. To be negative, this x has to be less than 2. which means we are to the left of 2. It looks like this might be a good time to split this into two one-sided limits, namely the limit as x approaches 2 from the left of that mess, x plus 2 times x minus 2 over the absolute value of x minus 2, and the limit as x approaches 2 from the right of the same expression. Okay, going back to the top one, remember, if you're approaching 2 from the left, so you're smaller than 2, think 1.99 or something like that, what's underneath here, inside the absolute value, is negative. So the effect of the absolute value is to negate what is inside of it. So we can write, since we are assured all of the x values we're talking about here are to the left of 2, we can write the following, replacing the absolute value with a multiplication by -1. And now we can see, sure enough, the x minus 2's can cancel, giving us the limiting value as x approaches 2 from the left of this x plus 2 that we had. But don't forget, that negative did not cancel away. We're still dividing by -1 or equivalently multiplying by -1. But this is just a polynomial. So I'm free to plug 2 in. And I get negative times the quantity 2 plus 2, or -4. But remember, that's just one side of things, right? That's the left-sided limit. What happens in the right-sided limit? Here again, what is the effect of the absolute value if I am assured I'm always to the right of 2, if I'm always a little bit bigger than 2? Well, this, like 2.1 minus 2, is always a positive value. And so the absolute value does nothing to positive things. It just leaves them alone. So we can rewrite this as limit as x approaches 2 from the right of x plus 2 times x minus 2 over exactly x minus 2. Notice we don't have the negative down here. Here again, these cancel. And we're left with simply x plus 2, again no negative. This again is the limit of a polynomial, so we're free to plug the 2 in. And we get 2 plus 2, or +4. Oops. Now, what happened here? The behavior on the left and the behavior on the right disagreed. That means this limit up here can't exist. We have a limit law to that effect. Look. We can only say this limit exists only if the left limit and the right limit agree in value. They both exist and agree. So we can say that this limit here does not exist. However, we can say more than just that. We can look at things graphically here as well. If I were to graph this function here, this guy right here, y equals x squared minus 4 over the absolute value of x minus 2, what this tells me, and in particular this here tells me, is I would see something like this. We have a graph, and I'm considering what happens as x approaches 2, so let me mark that. And this says, as I approach 2 from the left, so I'm coming in here like this, I'm shooting towards 2 from the left, my height, the height of the function, is getting arbitrarily close to -4. So let's indicate that here. There's a height of -4, and maybe I'm coming down, maybe I'm coming up. It's hard to tell perhaps, but I can say this much. I'm getting arbitrarily close to this height. I can't say what happens at 2. And in fact, if we go back to our original function here or here and try to plug 2 in, we get a 0 in the denominator, which of course we know messes things up. Okay. Down here, the right-sided limit tells us as I approach 2 from the right, as I come in this way towards 2, the height of my function is getting arbitrarily close to positive 4. So here's positive 4. As I come in from the right-hand side, I got to get arbitrarily close to that height. So whatever the rest of the function is doing, this is what it's doing right around 2. And of course, at 2, it's undefined. But you can see how the function's moseying along here, and then it gets to here, and then all of a sudden it jumps up to here and then continues on its way. There is a giant gap right here. And that's the graphical interpretation of what's going on. To be explicit, the graph of y equals x squared minus 4 over the absolute value of x minus 2 has a gap from 2, negative 4. Again, the 2 comes from here. The negative 4 being this one-sided limit value to 2, positive 4. Here again, that 2 and the positive 4 coming from the other one-sided limit value. Okay, so as for a value of this limit, it didn't exist, but that's the graphical interpretation. Okay, here we have a limit of a quotient. So again, we might be tempted to treat this with the limit law for a limit of a quotient of functions, rewriting it as a quotient of 2 limits, hopefully smaller, simpler limits. But again, we can only do that if the limit of the denominator is not 0. So we have to ask the question, what is happening to this? Where is it going? What is the limit as x approaches negative 1 of x plus 1 quantity squared? Of course, this is immediate, right? This is a polynomial when you expand it out, and so we're free to simply plug in negative 1. Of course, negative 1 plus 1 squared is 0. So our denominator is going to 0, which means we can't apply this quotient rule for limits. So we have to find another way to do this. Let's think about this expression for a moment. As you're considering x values that are getting very, very close to negative 1, what's happening to this x plus 1 squared? We said already it's getting very, very close to 0. And by virtue of the quantity being a square of something, can we tell what sign it is? It would have to be positive, right? So on the bottom, we have this fraction where we have a very tiny thing, something very close to 0, something very small, and we know that it's a positive value. On the numerator, we have a 1. Think about what happens here when this gets very, very small. Like if this is 1/1,000th, 1 over a millionth would be a million, right? And when this gets even smaller, say a trillionth, 1 over a trillionth is a trillion. The smaller this gets, the closer x gets to negative 1. The larger the whole fraction gets, the larger this gets. And in fact, by making the denominator as small as we want, by picking x sufficiently close to negative 1, we can make this overall fraction as large as we want. Graphically, what's going on here, let's mark negative 1 on our x-axis, as we get very, very close to negative 1 from either the left-hand side or the right-hand side, the closer we get, the larger this expression gets. So as I'm coming in this way, it's getting larger and larger, growing ultimately without bound. As we said, we could make it as large as we want, but getting close enough to negative 1. And the same thing happens on the other side. The closer we get to negative 1, the larger this thing gets, growing without bound. Of course, graphically, what we're describing here is a vertical asymptote. It is clear from this analysis that the graph of y equals 1 over x plus 1 squared has a vertical asymptote right here, at x equals -1. But if our function grows without bound the closer we get to -1, then there is no single height that I get arbitrarily close to. As such, this limit does not exist. The reason it does not exist, of course, again, is the function is flying off to infinity in a certain sense. It's growing without bound, as x is very near this point. We call such limits, even though they don't exist, infinite limits. Now, in the future, what we may do, actually we will do this, is in certain cases where it's clear that on both sides of the c value our x is approaching, if both sides agree in their nature, in other words, if they're both flying off to positive infinity, if they're both flying off in upwards direction, we might write something like this. Similarly, if they were both flying downwards, we might write this limit equals -infinity. But understand, infinity, whether it's positive or negative, is not a value. And technically, in both cases, this limit does not exist. Speaking more generally, whenever you're looking at a limit similar to this, where you have some sort of fraction, a over b, and in the limit, this numerator goes off to some number which is not 0, like 1, and the denominator goes off to 0, right? Positive small went off to 0 here. You can expect this to happen. You're going to have an infinite limit. The limit value does not exist, and you'll have some sort of vertical asymptote. Okay, and looking at this limit, we see that we're taking the limit of a composition. And the outer function is the sine function. We have limit laws for dealing with limits of compositions. This one might be relevant here. If we have the limit of a composition and this outer function f has this really nice property, we'll be able to pull out that f outside of the limit. This property says we can evaluate limits of the outer function by itself just by plugging in the c value in question. And as it turns out, our outer function, sine of x, has this property. Again, appealing to our limit laws, the limit as x approaches c of sine of x is sine of c. I can just plug this c in here. That allows me to take the sine outside of the limit. So I can write this much. However, once I get to trying to evaluate this inner limit, I run into a problem, right? Look at the denominator. As x goes to 0, doesn't that go to 0? And the numerator, of course being constant, is going to stay 1, or go to 1 as x goes to 0. This limit, consequently, is going to be an infinite limit. Or at least infinite on each side of 0. But that's enough to throw a big monkey wrench into this strategy for evaluating the limit. Let's think about what the graph of this function, y equals sine of 1 over x, is doing. Let's say that's 0. As x approaches 0, on one side, on the right-hand side, over here where x is positive, as x gets closer and closer to 0, this 1 over x gets closer and closer to positive infinity, right? It gets larger and larger. What happens when you take the sine of larger and larger values? Recall what the graph of sine looks like. something like that. And it repeats in both directions. So as we're talking about sine of larger and larger values, we're talking about the value of the sine, the height of this curve as we move to the right. Larger and larger x values. Larger and larger inputs. But the outputs we're seeing just go back and forth between 1 and negative 1. Consequently, in our graph, as x is approaching 0, as I'm moving this direction, I need to see all of these infinite oscillations bound together tighter and tighter so that they all might fit until our function is infinitely compressed at x equals 0. Similarly, on the other side of 0, if we were to approach from the left, so our x values are always negative, 1 over x is going to be large in magnitude, but negative still. And what happens when we get closer to 0 is that this gets larger in magnitude while staying negative. In other words, we're moving farther and farther left on this graph. So the sine values we get out, again, oscillate infinitely many times as they approach this 0 from the left. Again, being forced to bunch up until they're infinitely compressed right at 0. Even by our intuitive notion of a limit, if we were to cover up the behavior of this function at 0 and try to guess what this function's value should be there, under an assumption that it could be drawn with a single continuous stroke, we would have no idea. This is another case where this limit simply does not exist. And the reason this time is we have this infinitely compressed oscillatory behavior, notice with non-zero amplitude. Okay, so this limit does not exist, and there's the graphical interpretation and the reason for why it does not exist. It's worthwhile to point out, had we been looking at limit as x approaches 0 of the cosine of 1 over x, we would have seen the exact same behavior. This is getting very, very large. Maybe it's large and positive, maybe it's large and negative, depending on what side of 0 you approach. The cosine function also has this characteristic of if you go farther and farther to the right or farther and farther to the left, you just pick up repeated oscillations. So when we were to graph this, we get something very, very similar to what we see here in purple, with infinite oscillations happening in a very narrow band and resulting in a limit that does not exist. In looking at this limit, the limit as x approaches pi over 2 of cosine squared of 2x, we see that we're dealing with the limit of a composition. 2x is the innermost function in this composition, and then cosine is being applied to that, and then the outermost function is the squaring function. Now we have a couple of limit laws that deal with compositions of functions. Perhaps this bottom one is the most relevant. Notice this says, if you're trying to find the limit as x approaches something here of a composition where f is your outermost function, remember for us, f is the squaring function, then you can pull that outer function outside of the limit. If this is true, if that outermost function is such that finding limits like this, as x approaches c, can be done just by plugging c in. Is that the case here? Is it the case that the limit as x approaches c of our outermost function, that's the squaring function, could be obtained just by plugging c into this expression? Well, sure it is. This is a polynomial function. We know that's how we evaluate limits of polynomial functions. So that means we can pull this squaring piece outside of the limit. We can say all of this guy squared, where this, the inside here, is the limit as x approaches pi over 2 of cosine of 2x. Okay, that should be equivalent to that. Now, what about this limit? Here again, we have a composition of functions. Cosine is now on the outside. Is it true that we can evaluate this kind of limit just again by plugging in the c value into this function? Absolutely. Again, that's one of our limit laws. There it is right there. So again, we can pull out the outermost function here outside of our limit to arrive at that. Now notice this innermost thing here, this limit right here, is the limit as x approaches something of a polynomial function. 2x is a polynomial. So I am free to plug in pi over 2 in here to arrive at, and I'll write this as cosine squared because that's a little more natural, cosine squared of 2 times pi over 2. At this point the limits are gone. We just simplify this as a normal mathematical expression. That's cosine squared of 2 times pi over 2, or pi. This is cosine of pi squared, cosine of pi. Recall, if we consult the unit circle, there's 0, there's pi. I'm interested in the cosine here. Cosine, remember, is the x-coordinate, so it would be a -1 quantity squared, or 1. So that is the value of this limit. Now, notice, even though we used our limit laws to verify that this limit does indeed equal 1 step by step here, from a mechanical perspective, to arrive at this 1, we could have just plugged in pi over 2 into this expression. That's where we ended up here. In other words, if we look at this function, f of x equals cosine squared of 2x, then the limiting value as x approaches pi over 2 of that function, which is 1, and the value of that function at pi over 2, thus plugging it in to here, is also 1. When that happens, recall, graphically, we have a point of continuity on the graph. If we were to graph things, let's say here's pi over 2. The fact that this limit is 1 suggests we should be arbitrarily close to a height of 1 whenever we're sufficiently close to pi over 2, with the exception, perhaps, of what happens at pi over 2. Remember, the limit being 1 tells us nothing about the value of the function here. But knowing that we can plug this into the original function, into this function here, and also get 1, suggests that we can draw this with one continuous stroke. That this point is a point of continuity. And that's the graphical interpretation of what this limit is suggesting. That pi over 2, 1, remember pi over 2 is the x value, 1 is the height, the expected height of the function. The value of the limit here is a point of continuity on the graph of that function right there. So, value of the limit, graphical interpretation. That's it. Okay, here we have a limit of a quotient of two functions. And as such, your first impulse might be to try to apply the limit law for the quotient of functions, breaking it into a quotient of limits. But remember, we can only do this if the limit of our denominator is not 0. So we need to ask ourselves the question, what happens right here? What does this go to? What is the limit as x approaches 3 of x squared minus 9? But this is an easy question to answer, right? This is a polynomial function, and we know we can find limits of polynomial functions simply by plugging in the c value in question. So this should be 3 squared minus 9, or 9 minus 9, or 0. So the denominator does indeed go to 0, which means I cannot apply this. So I've got to find another way. Now, you might check out what is the limiting behavior of the numerator. It's fairly easy to spot. This is also a polynomial, and so we can, just like here, plug in the 3 into the polynomial to discover its limiting behavior, and 3 minus 3 is also 0. And when we see this 0 over 0 limiting behavior, frequently there is some sort of common factor that we can remove to make progress on evaluating this whole limit. Given that, and the fact that the denominator is very easy to factor, let's do just that. Okay, so factoring the bottom, we would have this identical to the limit as x approaches 3 of x minus 3 over x minus 3 times x plus 3. Remember, the bottom there is just a difference of squares. Of course, our natural urges should take over at this point. We like when things simplify, and so let's cancel the x minus 3's. And recall, we are confident we can do that because of this limit law right here. We're basically looking at two different functions that disagree at one point, namely at 3 itself. But they should share a common limiting value. Now, we're kind of back to where we began here. We're still looking at a limit of a quotient, but it's a different quotient. So maybe now my limit law for quotients does fit. Again, I need to look at the limit of the denominator. If it's not 0, I can use this limit law. So what is x plus 3 doing? Well, again, there's no need to write this, although I'll put it in red here. The limit as x approaches 3 of x plus 3, that's a polynomial. I'm free to plug in my 3. This is going to be 3 plus 3, or 6. Notice that goes to 6, and that is not 0. So I can indeed rewrite this limit of a quotient as a quotient of limits. And hopefully there'll be simpler limits. So we can rewrite this as the limit as x approaches 3 of the top over the limit as x approaches 3 of the bottom. And notice I've already done the bottom. That's sitting down here. That was 6. And the top is the limit of a constant function, which one of our other limit laws assures us is the constant itself. So this is just 1. We're done. That's the value of the limit. Now, keep in mind, graphically, if we look back at this original function, or the graph of y equals x minus 3 over x squared minus 9, let's draw a piece of the graph here. As x approaches 3, the fact that this limit is 1/6 suggests that if this is 1/6, I can get arbitrarily close to that height by staying sufficiently close to 3, with the possible exception of what happens at 3 itself. Remember, the limit doesn't tell you anything about what happens at that x value. And indeed, looking at this expression, I can't plug in 3 into this expression. 3 is not in the domain of this expression. So I do indeed have to leave this an open circle. We have a hole. More specifically, 3/1/6, that point. 3 being what x is approaching, 1/6 being the value of the limit. That point is a hole in the graph of this function. There's the value. There's the graphical interpretation. Okay, here in this limit, we again see a limit of a quotient. Again, we might be tempted to try to write the limit of a quotient as a quotient of limits. But we can only do that if the bottom in the limit is not 0. So, what happens in the bottom here? What does this go to? In the limit, as x approaches negative 3. Well, no need to write it down. This is a polynomial function. We can find its limiting value as x approaches negative 3 just by plugging in negative 3. So that becomes 9 minus 9, or 0. Well, that's a bummer, because that means we cannot use this limit law. We need to find some other way. Notice this denominator does indeed factor. Maybe that's the direction we should head. Let's play around with it a little bit. So we have x minus 3 over, of course, that's a difference of squares, x minus 3, x plus 3. And sure enough, we see something that we can cancel. So this is going to be equal to the limit as x approaches negative 3 of 1 over x plus 3. Now, what happens here? Here again, we have a limit of a quotient. Maybe it's time to pull this limit law out of mothballs here and apply it. Again, we need to make sure the denominator does not go to 0 if we're going to do that. So what happens to this new denominator? Well, same story really. This is a polynomial. I can find its limiting behavior as x approaches negative 3 just by plugging in x equals negative 3. Negative 3 plus 3, of course, goes to 0. And the numerator, by the way, is just always 1. So in the limit it would go to 1 as well, that being the limit of a constant function. Now, the presence of this non-zero number over 0 value as a limiting behavior for our fraction suggests that graphically we have some sort of vertical asymptote involved. You see, as this is close to 1 and this is close to 0, whether it be close to 0 and positive or close to 0 and negative, the resulting fractions are going to be very, very large, in magnitude anyways. Again, they could be positive or they could be negative. And the closer x gets to negative 3, the larger this fraction becomes in magnitude, either flying off to positive infinity or negative infinity. Let's get a little bit better idea of what's going on graphically. Here's negative 3 over here. If we are to negative 3's right, so we're over here somewhere and approaching negative 3, so like negative 2.99, notice the denominator is very small but positive. As long as we're to the right, this denominator will be positive. So we're looking at 1 over a positive small thing, which again, there are many, many small things you can take out of 1 here. This is going to be a large value overall. And because that's positive, and because that's positive, it's going to be a large positive value. So as I approach negative 3 from the right, my function has to get larger and larger, staying positive the whole while, and there's my vertical asymptote. As I approach negative 3 from the left, so for example, I'm coming in here, maybe I hit negative 3.1. Negative 3.1 plus 3 is a small value, yes, but it's small and negative. So we have 1 over a small negative. And that's always the case if you're to the left of negative 3. This denominator is always negative, which forces the whole fraction to be negative since the top is positive. Now, as x gets closer to negative 3, this gets smaller and smaller in the denominator, which makes this whole fraction larger and larger in magnitude, and yet it is always negative. So as we move to the right, getting closer and closer to negative 3, we're getting larger and larger in magnitude, but staying negative, which means we're going down, flying off to negative infinity. And we have the vertical asymptote there as well. Okay, so it should be clear from the graph, or from this calculation up here, that this limit certainly does not exist. Infinite limits are certainly involved, as the function flies off to both positive infinity on the right and negative infinity on the left. And graphically, we say we have a vertical asymptote. Okay? So the limit does not exist, there's infinite limits involved, and we have a vertical asymptote at x equals, negative 3. That's it. Okay, in this limit, we have the limit of a quotient. And again, we might be tempted to try to use the limit law for quotients, splitting it up into a quotient of limits. But that only works if the denominator in the limit is not 0. So we need to ask the question, what happens to our denominator in the limit? But that's pretty clear, isn't it? This is a polynomial function, so we can find the limiting value just by plugging in this 4. That's 4 minus 4, or 0. So we cannot use this quotient rule for limits, as we have not satisfied this condition. So we've got to try something else. One thing you might ask yourself is, if the denominator here is going to 0, what's happening to the numerator as x goes to 4? In other words, what is the limit as x goes to 4 of 2 minus the square root of 8 minus x? Now, you should eventually get to the point where you can see that you can evaluate this limit just by plugging in x equals 4. And we're going to do that here. So this would be 2 minus the square root of 8 minus 4, or 2 minus the square root of 4. Oops, there's my minus. Or 2 minus 2, or 0. But if that didn't make sense as to why we could simply plug in our x equals 4 to get this limiting value, I promise I'm going to come back to this at the very end of the problem and clear that up. Okay? But notice this also goes to 0. When that happens, you have this 0 over 0 limiting behavior. Frequently, you can find a common factor in the numerator and denominator that you could cancel off to make further progress towards evaluating this limit. But how in the world do we find that common factor here? It requires a bit of a trick. What we're going to do is rationalize not the denominator, but the numerator. We're going to get rid of the radicals present in the numerator. And a way we could do that is to take this expression here, which is 2 minus the square root, or some a minus some b. If we could only multiply that by 2 plus the square root of 8 minus x, right? A minus b times a plus b is a difference of squares. That'd be a squared minus b squared. You'd have to square this, you'd have to square this, which would get rid of the radical, and there'd be no more radical left. Okay? We'd really like to multiply the top by that. But doing so would change the overall expression, so instead I multiply by this over itself. So now I'm just multiplying this expression by some well-chosen value of 1. And that shouldn't change anything. So doing the multiplication, we now have the limit as x approaches 4 of this times this, which is this form here. First guy squared, 4 minus second guy squared. Don't forget to put it in parentheses lest you lose a distributed negative there. But that squared is simply 8 minus x over the bottom, which I'm going to leave purposefully in factored form. Now, why would I not multiply it out? Remember, I'm hoping for some factor in the numerator and denominator to cancel. Right here, there is only a factor of x minus 4. That's the piece that's going to 0. That's the factor right there that I want to cancel off, ultimately, so that I don't have a limiting behavior of 0 in my denominator, and I finally can use this limit law dealing with quotients of limits. So if I'm trying to cancel it off, I'm going to leave the bottom in factored form, so that's easily done. Now, looking at the numerator, our urge to simplify should take over. We have the limit as x approaches 4 of, let's see, this is 4 minus 8, that's a negative 4. We have a negative x there, that's a positive x. I could write plus x, or I could just put the x here. That maybe looks a little prettier. And then that's sitting over x minus 4 times this mess right there. But notice, there's our cancellation. That's what we hope to see. So this should be then the limit as x approaches 4 of 1 over 2 plus the square root of 8 minus x. Again, we're back to a limit of a quotient. Maybe now we can use this rule. It depends. What's happening to the denominator? Is it going to 0? What's happening to this? And just like this one, we discover that we can find the limiting value as x approaches 4 of 2 plus the square root of 8 minus x simply by plugging it in. And again, I promise to explain why this is true in just a second. So 2 plus the square root of 8 minus 4, which is 2, plus the square root of 4, which is 2, plus 2, which is 4. Notice that is not 0. So I am free to break this into a quotient of limits, namely the limit of the top, which is easy, that's just 1, and the limit of the bottom, as x goes to 4, which we just figured out was 4. So that is the value of the original limit. Now, the limiting value did exist, we got 1/4, but the original function involved, this guy right here, doesn't exist when x actually equals 4. So graphically, if here's 4, we can expect a limiting height of 1/4, which means our graph looks something like this. But at 4 itself, because we had a 0 in our denominator here, this is undefined. Okay, so graphically we have a hole. Okay, at 4, 1/4. 4 again coming from here, 1/4 being the value of the limit. So that's the value, that's the graphical interpretation. This problem is effectively done, except for I want to go back and just illustrate why we knew we could just plug 4 in to evaluate both of these limits. Let's just take one of them, and then the argument for the other will be clear. First, looking at the limit as x approaches 4 of 2 plus the square root of 8 minus x, so we're looking at this one here. Notice we're looking at the limit of a sum. But we have a limit law for such things. The limit of a sum of two functions can be written as the sum of the limits of those functions. So we can break this apart. So this is the limit as x approaches 4 of simply 2 plus the limit as x approaches 4 of the square root of 8 minus x. Now the first one is easy. The limit of a constant is that same constant value. So that should be 2 right there. This one is the limit of a composition. And we have a couple of limit laws related to compositions, this one being a really nice one. If you see an outermost function in our composition such that this is true, we can pull that outermost function out. Now, is this true? Can I evaluate a limit as x approaches any c of the square root of function just by plugging the c in, as long as it's a reasonable value of c? And sure enough, we can. That's basically what this says. So, I can rewrite this as the square root of the limit as x approaches 4 of 8 minus x. Finally, we're down to a polynomial function that we're taking the limit of, and we know we can simply plug in 4 there. So this becomes 2 plus the square root of, and now plugging 4 in here, 8 minus 4, which you notice is exactly what we had there, and the result of simply plugging 4 into the original expression. Okay, so both of these were legitimate moves to make. Going back to the original limit, there's the value, there's the graphical interpretation, we're done. Okay, here we're after the limit as x approaches 0 of some f of x, where f of x is this piecewise defined function. Notice, as x approaches 0, it might be bigger than 0, it might be less than 0, and depending on which is the case, changes which expression we use for f of x. So perhaps here it's better to split things up into what's happening as we approach 0 from the right and what happens when we approach 0 from the left to f of x, noting that only if these things agree, right, here we go, do we have a common limit, overall limit value. So only if the limit coming in from the left and the limit coming in from the right exist and agree, can we say this? Okay, so what is this limit as x approaches 0 from the right? Well, if we're approaching 0 from the right, we're always positive, we're always bigger than 0. Which piece applies? That would be this one. So I can replace f of x with e to the x. Now, how do we find this limit? Well, consider the limit laws. We know that the limit as x approaches c of e to the x must be e to the c. So if it's the case in the general limit as x approaches c from either direction, it certainly must be the case as we approach from a single direction. So this has to be e to the 0, or 1. So that's the behavior on the right side. Down here, if we're approaching 0 from the left, we're always less than 0, which means this piece applies, and f of x is identically x plus 1. So we can make that substitution. This must be x plus 1 here. But again, this is just a limit of a polynomial, so we can just plug in our value 0 to get 0 plus 1, or 1. Notice, both of the one-sided limits existed and they agree in value, which means this overall limit is that same value. Now, what's going on graphically? Well, we have to look at the limit and what that tells us. If we were to graph this thing, here at 0, we would expect to be 1 high. So we would get arbitrarily close to a height of 1 coming in towards x equals 0 from either the left or the right. But I can also figure out exactly what happens at 0. You see, 0 is covered by this condition. F of 0 is e to the 0, because this condition applied. So f of 0 equals e to the 0, which is also 1, which means I need to fill this point in, which means I can draw this curve, at least right around 0, with a single continuous stroke of the pen. We have a point of continuity at x equals 0. More specifically, the ordered pair here, 0, 1, 0 again coming from here, 1 coming from here. That is a point of continuity on the graph of y equals f of x, where this is f. That's it. Value, graphical interpretation.